Predictive modeling is the practice of using historical data to forecast future events or behaviors. Imagine a retailer who wants to know how many units of a new product will sell next month. By feeding past sales, price, promotion, seasonality, and economic indicators into a statistical or machine learning algorithm, the retailer creates a model, a set of mathematical rules that can generate a sales estimate for the upcoming period. In business analytics, the scope goes beyond sales. It includes churn prediction, credit scoring, demand forecasting, fraud detection, and workforce planning. The model is a crystal ball that turns raw data into actionable insight, allowing managers to allocate resources, set targets, and mitigate risk before the event actually happens. Supervised learning is like a teacher grading essays. The algorithm receives input-output pairs features and the correct answer and learns a mapping so it can predict the answer for new inputs. Example, a bank supplies a data set of loan applicants with attributes income, credit score, debt, and a label default or no default. The algorithm learns to predict default for future applicants. Unsupervised learning has no teacher, it only sees the inputs and tries to discover hidden patterns like grouping customers with similar purchasing habits, clustering, or reducing many variables to a few underlying factors. Principal component analysis. Business use cases: supervised email spam detection, demand forecasting, unsupervised market segment discovery, anomaly detection for fraud, product recommendation based on similarity clusters. The key difference is whether you have a known target variable to predict supervised, or you are exploring the data to find structure unsupervised. Linear regression assumes a straight-line relationship between a dependent variable y, for example sales, and one or more independent variables x1, x2, xp, such as price, advertising spend, or season. The model can be written as y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus plus beta p times xp plus epsilon, where beta 0 is the intercept, beta I are the coefficients that measure how much y changes when xi changes by 1 unit, and epsilon is the random error term. To derive the coefficients, we use the least squares method. Choose beta values that minimize the sum of squared residuals sigma of open parenthesis yi minus y hat I close parenthesis squared. In matrix form, beta hat equals open parenthesis x transpose x close parenthesis to the minus 1 power times x transpose y. Interpretation: if beta 2 equals 3, then holding everything else constant, a $1 increase in advertising spend raises expected sales by 3 units. The model also gives a R-squared statistic that tells what proportion of variance in Y the model explains, a useful how good is it check for managers. Classification predicts a categorical outcome, for example whether a customer will churn, yes or no. Logistic regression transforms the linear combination of inputs into a probability using the sigmoid function. P equals 1 over 1 plus e to the negative beta 0 plus beta 1 x1 plus beta p xp. The probability p is then thresholded, commonly at 0.5, to assign a class label. Logistic regression is easy to interpret. A positive beta I means higher xi raises the odds of the positive class. Decision trees split the data recursively on the feature that best separates the classes, measured by impurity criteria such as Gini index or entropy. Think of a flowchart. If income greater than 70,000, then go left, else go right. If recent purchases greater than 5, then predict churn, else not. Trees are intuitive for managers because the rules can be read directly, but single trees can be unstable. Small data changes may produce a very different tree. Ensemble methods such as random forest and boosting combine many trees to improve accuracy. Model evaluation tells you how well a predictive model performs on unseen data. Accuracy equals TP plus TN over TP plus TN plus FP plus FN, overall fraction correct, but can be misleading with imbalanced classes. Precision equals TP over TP plus FP. Of the cases predicted positive, how many are truly positive? Useful when false positives are costly, for example sending a marketing offer to non-responders. Recall, also called sensitivity, equals TP over TP plus FN. Of the actual positives, how many did we capture? Important when missing a positive is expensive, for example, fraud detection. F1 score equals 2 times precision times recall divided by precision plus recall, a harmonic mean that balances precision and recall. ROC curve plots true positive rate, recall versus false positive rate, which equals FP over FP plus TN for different thresholds. The area under the curve AUC summarizes overall discriminative ability, 1 equals perfect, 0.5 equals random. Managers can pick the metric that aligns with business cost structure. Overfitting happens when a model learns noise in the training data, performing great on that data but poorly on new data, like memorizing every answer on a practice test instead of understanding the concepts. Underfitting is the opposite. The model is too simple to capture patterns, similar to using a straight line to fit a clearly curved relationship. The bias variance trade-off captures the tension. High bias, simple model leads to systematic errors. High variance, complex model leads to sensitivity to data fluctuations. Regularization adds a penalty to the loss function to shrink coefficients, controlling complexity. Ridge, L2, adds lambda times the sum over j from 1 to p of beta j squared. It keeps all variables but reduces their magnitude. Lasso, L1, adds lambda times the sum over j from 1 to p of absolute beta j. It can drive some coefficients to exactly 0, performing variable selection. The tuning parameter lambda determines the strength of the penalty. Larger lambda leads to more regularization. Cross-validation estimates how a model will perform on unseen data by repeatedly splitting the data into training and validation sets. K-fold CV, the data set is divided into K equal parts folds. The model is trained on K-1 folds and validated on the remaining fold. This process repeats K times so each fold serves as validation once. The average metric across folds is the CV score. Typical choices, K equals 5 or K equals 10. Leave one out CV, LOOCV. A special case where K equals N the number of observations. Each observation is left out once as the validation set, and the model is trained on the remaining N-1. LOOCV uses almost all data for training each time, giving low bias but high variance and high computational cost. Managers use CV to compare competing models, for example linear versus tree, and to select hyperparameters like lambda in regularization that give the best expected performance. Feature engineering is the art of creating useful inputs for the model. The common steps are cleaning, handling missing values, imputation, and removal. Transformation, scaling, standardization, and min-max so that algorithms treat variables comparably. Log transforms for skewed data, for example sales dollars. Encoding, converting categorical variables into numbers, one-hot encoding and target encoding. Interaction terms, multiplying two variables to capture joint effects, for example price times promotion. Temporal features, extracting day of week, month, holiday flags from timestamps. Variable selection strategies include filter methods, correlation, and chi-square that rank variables independently of the model. Wrapper methods, forward and backward selection, that evaluate subsets using model performance. Embedded methods, lasso and tree-based importance, that incorporate selection during training. Good feature engineering often yields bigger gains than sophisticated algorithms, and managers should allocate time and resources to understand the business meaning of each feature. Predictive analytics can go wrong if managers overlook common pitfalls. Data leakage, using information that would not be available at prediction time, for example including future sales in a training set. Sampling bias, training on a non-representative subset, for example only loyal customers, leading to poor generalization. Over-reliance on historical patterns. Markets evolve, so a model built on past data may become obsolete. Ethical considerations. Fairness, models must not discriminate on protected attributes such as gender or race. Techniques like disparate impact analysis and bias mitigation are essential. Transparency, stakeholders need understandable explanations, especially for high-stakes decisions such as credit or hiring. Simple models or model-agnostic tools such as LIME or SHAP help. Privacy, handling personal data must comply with regulations such as GDPR or CCPA, and follow anonymization best practices. Managers should embed governance processes, including data auditing, model monitoring, periodic retraining, and a clear escalation path when model outputs conflict with